Computing Moments about the mean exercise. This is part of week 4, expectation in the method moments. So if you go to the REPL for that exercise, you get this preloaded code here. You're given 4 initialized sums. You're given 3 moments, and namely the second, the third, and fourth moments that you need to compute. And the task for this exercise is to draw a graph showing how the values of these moments, the second, the third, and the fourth moment, how these moments about the mean depend on the number of samples they're computed from. So we're basically doing a similar thing to the previous exercises that we've done, in that we are assessing how the size of the sample of random variables that we compute moments from affects the estimate for that moment. So what we want to do now is, firstly, we need to modify these variables here in order to give us the result that we want. Okay. The first step is to set the first element of the list equal to 1, second equal to 2, and so on, which we do as such in the for loop. Say that indices I is equal to I plus 1. So the ith index, the ith element of indices is equal to I plus 1. That way we have 1 to 200 including. Okay, and then second step, set the first element of the list called C moment 2 equal to a second moment about the mean, calculated by generating one uniform random variable that lies between 0 and 1. The second element of the list should be equal to a second moment about the mean, calculated by generating 2 uniform random variables, and so on. Okay, so this is the general formula for the rth moment here. This is actually the whole thing is the expectation for the rth moment, and the expression within the curly braces here is the actual expression for the moment that we're going to use. So what we're going to do now is we're going to populate the list called C moment 2. But before we do that, we need to look into what actually goes into calculating a moment. So to calculate a moment, you need a sum, and then you use that sum to divide over the number of elements that you have. That's what a moment is. So what we want to do now is we want to populate the first sum, so sum 1, and we need to add to it the value of my var here, which is set equal to a uniform random variable between 0 and 1, which is exactly the type of variable that we want to use. And then second sum, which is the sum that we're going to use for the second moment, is this sum here. So the sum over n elements of x sub I minus the sample mean, which is denoted by x bar here, all squared. So for each iteration of this loop, we're going to add to it the expression that's within the curly braces squared. So xi, x subscript I is the actual is the random variable that we want to assess. So xi here is my var, and then x bar is the sample mean that we have so far computed from our list, and that we can describe as sum 1 over indices I. So that's the sum of the individual uniform random variables that we've added up so far over the amount of them that we have so far. So that's the sample mean that we have so far. Okay, then what we want to do is, for the second sum, we want to square it. So now we have an expression that is equivalent to this expression here, the one inside the brackets, including the power. Now we want to do a similar thing for the third and the fourth moments, which we can do as such. Now, since the rth moment is described here, where here r is equal to 2, so ur is u2, mu r is mu2, where 2 is the order of the moment. So so if r is 2, then we're calculating the second moment. If r is 3, then it's the third moment, and so on. And here r is equal to 2, and when we want the general moment or the rth moment, we just raise this sum here, this expression here, to the power of r. So that's exactly what we're going to do here. I'm just going to take the sample mean, which is sum 1 over indices I, and we're going to divide that, we're going to raise that to the third power, because we're calculating the third moment. You just have to be careful with your brackets, so you don't include the power where it shouldn't be, and you can avoid that just by copying the expression as such and just changing the number. So a similar process will be done for the fourth moment. You just raise that to the fourth power, and then once you've done you've completed all the moments, you've completed the indices, you've used up all the initialized variables that we have here. This code will then plot the rth moments against the indices and generate a graph. Okay, it seems to produce a straight line for some reason. Okay, the third moment works, but the second and fourth don't work. The problem is that I didn't define the actual moments, I just got the sums. So what we want to do is, since we've defined all the sums, we need to now define the moments. And so since the C moment, all of these moments are just a numpy arrays, what we're going to do is that for each element in that numpy array, we're going to assign it the value of the respective sum over the indices. Over indices I, which is the number of elements that we have thus far. We're going to repeat the process for the third and fourth moments. And using this, the averages should change. Yep, and passes the tests. So if you want to, if you've plotted a graph and it turned out to be false, what you can do is you can just change the name and then run it again, and it will produce a different PNG file, and you can see the actual results again, or the results of running the test, running your code on a different PNG file, and this is the result that we want. And then just to make sure that you don't fail the test when you run them, you need to change them back to the original name. And as you can see, you run your test again, and this doesn't work because, again, it's a probabilistic test. It's a very low chance that it might not work. Just run it again. Hit submit, run the tests a final time. You see, it keeps happening. And they check out after some struggle. So that was computing moments about the mean, using summations and exponentiation to the rth power.